Bismillahirrahmanirrahim. Assalamu alaikum. Today, this is our lecture 6A. In our previous lecture, we discussed about topological indices of some graph operations, and from now and in further lecture, we will discuss about extremal graph theory with respect to topological indices. So, this is our contents of today's lecture: introduction, our goal, behavior of degree and distance based topological indices when we add an edge. This is our content of today's lecture. Let's start with some introduction about the extremal graph theory. So what we say, extremal graph theory is about finding the value of finding the graph from a set of graphs which gives the maximum and minimum value for some graph parameter. This graph parameter could be the number of edges, radius, diameter, or some topological index. So in short, extremal mean we find two extremes which gives the minimum and which gives the maximum value. So as we are discussing about topological indices, so our main concern will be finding the extremal graph from a set of graph. We have a set. From that set we investigate the graph which gives the maximum and minimum value for some topological index. For example, we have a set of graphs on n vertices, set of all graphs. Of course, when we talk about graph, our meaning is the graph is finite, connected, and simple. So we have a set of graphs we have set of all graphs. All graphs mean finite, simple, undirected graphs, and we need to investigate the graph which gives the maximum number of edges from that set and which gives the minimum, which contains the minimum number of edges in that set. And we know that the complete graph on n vertices contains the maximum edges because every two vertices are adjacent with an edge, and any tree contains the minimum number of edges. So for this question, the extremal graph, the graph with maximum edges is a complete graph, and the graph with minimum edges is any tree. Here we have n into n minus 1 divided by 2 value, and here we have value is n minus 1, and all other graphs contains number of edges between these two numbers. So the minimum value for this question, I mean we are talking about the graph with minimum edges and the maximum edges. So minimum range is n minus 1 and the maximum value is n into n minus 1 divided by 2. So this is a simple example about the extremal graph. Here we have another example about the diameter. So if we talk about the diameter, we know that the path graph has the maximum diameter, and the complete graph has the minimum diameter, because in complete graph the maximum distance between two vertices is 1, while in the path graph the maximum distance between two vertices is n minus 1, the last and the first vertex if we consider. So diameter here could be n minus 1 and here is 1. So all other graphs have diameter between 1 and n minus 1. So this is a very simple introduction of extremal graph theory, and this is about finding the values, extremal values, I mean maximum value and the minimum value, and the corresponding graphs, which graphs attains the maximum value and the minimum value. So what is our goal with respect to our subject? I mean we are discussing topological indices of chemical graphs. So our main aim is that we have a set of graphs and we need, or we are interested to find the extremal graph extremal graph with respect to some topological indices. I mean, if we talk about, uh, we talk about the first Zagreb index, and we have a set of graphs, and that set could be depend upon the number of vertices and the radius, and number of vertices and the diameter, and other, and we can consider in that set some other parameter, and we are interested to find the maximum and minimum value of the first Zagreb index and the corresponding graph, which is very important. I mean, which graph attains the maximum first Zagreb index, and which graph attains the minimum Zagreb index. So our goal is about study the extremal graph with respect to topological indices, and these topological indices could be degree or distance space. Okay, very quickly, the some application why we study extremal graph theory for topological indices. Extremal graph theory for topological indices can help to predict the molecule with extremal properties. I mean, we want to we want to check which molecule give the maximum boiling point. So maybe the first Zagreb, the graph with maximum first Zagreb index attain the maximum boiling point. Similarly, the melting point and other physical or chemical properties. So in this way, the extremal graph theory for topological indices can help chemists and pharmacists to investigate the graph with extremal property. So let's discuss behavior of degree based topological indices when an edge is inserted in a graph. The topic of extremal graph theory, we start to discuss the extremal graph theory with this very basic idea: inserting an edge between two non-adjacent vertices. So we have our first question: investigate the behavior of the first Zagreb index when an edge is added between two non-adjacent vertices of G. So in other words, what happened when an edge is added between two non-adjacent vertices of G to the first Zagreb index? I mean, either first Zagreb index increases, either first Zagreb index decreases, or it remains same. So let's check the behavior of the first Zagreb index. So before checking the behavior, we discuss about the notation of adding an edge. What is the meaning of adding an edge? Let G be a graph with non-adjacent vertices u v. I mean, there is no edge between u and v. So we have a graph G with non-adjacent vertices u and v. We construct a new graph by inserting an edge between u and v, which is G plus uv. So now we have two graphs, G and G plus uv. We need to compare these two graphs with respect to first Zagreb index. Okay, for comparing the first Zagreb index, let's discuss the degrees of vertices in G plus uv. So degree of v in G plus uv is equal to degree of v in G plus 1, and the degree of u in G plus u is equal degree of u in G plus 1. Why this happen? And all other vertices, the degrees of all other vertices remain same. You can see here that the degrees all other vertices are same as in G and G plus uv. Why this happen? Let's see here. This is our G, and when we add, this is our u, this is our v, this is our u and v. When we add an edge between u and v, their degrees increases by 1, and all other vertices, I mean, if this is x, all other vertices remain same. The degrees of all other vertices remain same. So this is our new graph G plus uv. So this result is very important to compare the degrees of to compare the first Zagreb indices of these two graphs, I mean G and G plus uv. So Again, please remember this, the degrees of u and v only change, and the degrees of all other vertices remain same. So now we investigate the behavior of first Zagreb index m1 of g minus का first Zagreb index of g plus uv. In first step, this is exactly the definition of first Zagreb index for g and g plus uv. We break the summation in such a way that this summation contain all the vertices with same degrees, whose degrees are all unchanged or unaltered. So all the vertices with same degrees, and the degrees of u and degree of u in g plus degree of v in g. We are considering u and degrees of u and v separately because these two vertices have different degrees in g and g plus uv. And similarly, we break the summation of g plus uv. Here we have g plus uv. In this summation, all the vertices with unchanged degrees minus degree of u in g plus u minus degree of v in g plus u. As we noticed in previous result that the degrees of all the vertices except u and v are same, so we cancel out these and we remain this in our next step, degree of u, degree of v minus degree of u plus 1 minus degree of v plus 1 square. And clearly we can notice that this term is less than 0. So we here we compare the first Zagreb index of g and g plus u. So what we conclude from this discussion? From the above discussion, we can notice that the first Zagreb index of g is less than the first Zagreb index of g plus uv. So what we observe from here, that adding an edge between two non-adjacent vertices increases the first Zagreb index. You can see from this result we can conclude that adding an edge increases the first Zagreb index. After this discussion, a question arises. What is the question? Let G be the set of all graphs on n vertices. Investigate the graphs which gives the maximum and minimum first Zagreb index. I mean, we have a set of all vertices on n, a set of all graphs on n vertices. We are interested to find the maximum and minimum value of the Zagreb index, and which graph attain the maximum value and which graph attain the minimum value. Okay, let's discuss this. As we noticed in our previous discussion that the first Zagreb index increases as the number of edges increases. So we can conclude that as much as we have edges in our graph, the first Zagreb index will be the maximum. Or in other words, we can say that the maximum Zagreb index is attained by the complete graph, because complete graph has the maximum number of edges. And in other and that trees, because trees has minimum number of edges, so among the graphs of order n, trees attain the minimum first Zagreb index. And we have a next result here. The first Zagreb index is given by the maximum is given by the complete graph, and the minimum first Zagreb index is given by the tree. This the first Zagreb index of a complete graph is given by the formula. We have here n vertices, and every vertex has degree n minus 1 whole square. So this is the formula of first Zagreb index of complete graph, which is the maximum first Zagreb index. All other graphs have less, or all other graphs have less first Zagreb index. Here another question is arise that which trees, because tree itself is a class of graphs, so which trees attains the maximum and minimum first Zagreb index. So we have another question here, which tree gives the minimum and the maximum first Zagreb indices. So we will discuss this question in later lectures, but this is very interesting and important exercise to investigate the tree, which tree gives the maximum and minimum value. So in this slides we discuss about adding the adding effect of adding an edge between two non-adjacent vertices for first Zagreb index, and we get that the complete graph gives the maximum value. So here are some exercises for you to get some foundation on the subject. Check the behavior of the second Zagreb index, inverse degree sum index, standard index when an edge is added, or of course investigate which graph gives the maximum and minimum value for these topological indices. So you must consider the definition before finalizing the result, because sometimes adding an edge increases the topological index, and sometimes adding an edge decreases the topological index. So it depends upon the definition of the topological index. So you must try these exercises. Next we will discuss about behavior of distance based topological indices when we add an edge in graph G. So similarly we have a graph G and a new graph G plus U. This time we can notice that adding an edge between two non-adjacent vertices U and V reduces the distance at least between U and V. Clearly we can notice that. Or in general we can say that adding an edge may reduce the distance between two vertices of G. I mean, maybe there are some vertices whose distance remains same after adding an edge, but at least there are two vertices U and V there whose distance is now 1 after adding the edge. So distances in G plus U, distance between U and V in the graph G plus U is less or equal to distance between U and V in G. How this work? Let's see. We notice that this is our U, V, W and X vertices, or we can say these are written, but there is no edge between U and V. So at this time, if we notice that the distance between U and V is 1, 2 and 3, but when we add an edge between U and V, the distance is now 1. And so distance between U and V is reduced in G plus UV, and the distance between W and X, if we check, the distance between W and X is 1 in G, and it remains same in the graph G plus W. So the distance for the distance between W and X is same in G and G plus UV. So we can say the distance between two vertices may reduce when we add an edge between two non-adjacent vertices. So we discuss about the Wiener index of G and G plus UV. From above discussion, of course, from above discussion we can easily notice that adding an edge will reduce the rending index, because rending index depend upon the distances between vertices, and as we are adding edges between two non-adjacent vertices, so the distance is now becoming reduces between two vertices. So we can notice that by inserting new edges, the Wiener index is decreases, and we know that the complete graph attains the maximum number of edges, so the Wiener index of complete graph is minimum, while the winner index of a tree is maximum. Of course, this is another question, which trees attains the maximum or minimum winner index. But when we talk about when we talk about the graphs on n vertices, the complete graph attains the minimum winner index, and tree attains the maximum winner index. As we discuss, adding an edge decreases the winner index. Or on the other hand, the Harary index increases as we adding an edge, because the term is now it is in reciprocal. That's why Harary index increases. This is the definition of the Harary index. UV subset of vertex set of V. So this is the behavior of the winner index when we add an edge. So in this way we obtain the extremal graphs. In this case, complete graph gives the minimum in case of winner index, and tree gives the maximum. Some more questions and exercise for you. Check the behavior of some eccentricity based topological indices. In this lecture we didn't discuss any eccentricity based topological indices, but this is very easy because eccentricity depends upon the distances between vertices, and we discuss the behavior of distances when we add an edge. So you can easily discuss the eccentricity based topological indices when we add an edge between two non-adjacent vertices. Some other exercises for you. Let S be a set of simple, finite and connected graphs on 4 vertices. Find which graph will give the minimum and maximum first Zagreb index. So now we have set A4. I mean all graphs which are simple, finite and connected, and find which graph attains the maximum and minimal first Zagreb index, of course with some reasons. Last question, question 3. Let T for 10, I mean this is just a notation, be the set of trees of order n with 4 pendant vertices. Here is a set of all trees of order n, with 4 pendant vertices. I mean every tree in this set is of order 4, and out of 10 vertices 4 are pendant vertices. Investigate the graph which gives the minimum and maximum first Zagreb index. One example of such a tree is, I mean 1 2 3 4 5 6 7 8 9 10. You can see we have 4 pendant vertices and overall order is 10. So this is one graph. There are many other graphs like 2 3 4 5 6 7 8 9 10. So there are many other graphs which are of order 4 with 4 pendant vertices. Our goal is to investigate the trees with maximum and minimum first and second Zagreb indices. This is very particular question we are discussing in this lecture, because we are just starting started to study this topic, extremal graph theory with respect to topological indices. Generally we will do it in general way, which we will do it inshallah in our next lecture in generalized way. So another question, G38 be the set of graphs of order 8. Okay, so we made another set here. Let G38 be the set of graphs of order 8 with radius 3. Investigate the extremal graph for the winner index. Again, this set contains many graphs, and we need to find the graph with maximum and minimum winner index. Of course, there are 2 questions. First, we need to investigate the extremal values. Remember extremal values. First, we will investigate the extremal values, I mean maximum value and the minimum value, and second, extremal graphs. Extremal graph mean which graph attains the minimum value and which graph attains the maximum value. So this is a very short today's lecture on the extremal graph theory for the topological indices. So we will discuss further on this topological indices in our future lectures. So if you have some comments, you can if you have any suggestion, comments or exercises, you can contact me on my email address, which I shown you on very first slide, and further discussion we can do it in our classroom. So for the next lecture, till Allah Hafiz.